Every human who has ever lived has felt the same quiet moment at night. You step outside. The air is calm, the world is silent, and above your head is a sky filled with lights so distant that your brain cannot really understand what you are looking at. Those lights are not decorations, they are suns. Some of them died before the pyramids were built. Some of them are still being born right now inside giant clouds of gas that stretch across hundreds of trillions of kilometers. And somewhere out there, objects drift between those stars. Not planets, not asteroids tied to any system. Just silent travelers moving through the darkness for millions, sometimes billions of years. Most of them will never come near us, but every once in a while, one does. And when it happens, the first people to notice are not astronauts. They are quiet astronomers, staring at computer screens in rooms full of blinking data, because space rarely sends visitors. But when it does, those visitors sometimes behave in ways that make scientists stop talking, not because they are hiding something, but because they simply do not understand what they are seeing yet. This story begins exactly like that, with a signal inside a database, a moving dot, an object traveling faster than anything that should naturally exist inside our solar system. The system that detected it was not built to find aliens or strange cosmic machines. It was built for something far more practical, protecting Earth. The network is called ATLAS. Asteroid, terrestrial impact, last alert system, a group of telescopes scanning the sky every night, searching for rocks that might be heading toward our planet. Thousands of objects appear in their data every year. Most are harmless. Some are interesting. Almost all of them follow predictable paths. But one night, the computers flagged something unusual. An object was moving far too fast. Its trajectory did not match anything bound to our Sunday. When astronomers calculated its orbit, the number that appeared on their screens immediately told them something important. This object did not belong here. It came from somewhere else, outside our solar system, an interstellar visitor, the third one ever confirmed. They gave it the name 3I, Atlas, the third interstellar object. At first, scientists were excited. These things are incredibly rare. Before 2017, humans had never confirmed even one. Then came the first known visitor, Oumuamua, detected by the Pan-STARRS Observatory in Hawaii. A strange object that did not behave like a normal comet or asteroid. It accelerated slightly as it left the Sunday. No visible gas jets. No clear explanation. The debate around it lasted years. Then came the second visitor, 2I Borisov, discovered by amateur astronomer Gennady Borisov. A true comet. Ice, dust, gas clouds. Exactly what astronomers expected an interstellar comet to look like. That discovery reassured scientists. Maybe Oumuamua was just unusual. Maybe the universe was not throwing strange surprises at us after all. But when 3I, Atlas, appeared in the sky, that sense of comfort started to fade. Because almost immediately, the numbers looked wrong. Its speed entering the solar system was enormous. More than 60 kilometers per second relative to the Sunday. That might not sound dramatic, But in cosmic terms, it is extremely fast. Too fast for something that formed here. It was clearly an outsider. A traveller that had spent millions of years drifting between stars, and now it was passing through our cosmic neighbourhood. The first images came from telescopes that have watched the sky longer than most people have been alive. The Keck Observatory, 2 giant mirrors sitting on top of Mauna Kea in Hawaii. Each mirror 10 meters wide, powerful enough to see faint galaxies billions of light years away. Astronomers pointed Keck toward the new object and started gathering light. When scientists observe something that far away, they are not really looking at pictures. They are looking at data. Every photon of light is information. And when that light is split into colours using spectroscopy, it reveals chemical fingerprints. Water, carbon dioxide, methane, ammonia, the basic ingredients of comets. At least, that is what researchers expected to see. But the fingerprints were weak, unusually weak. Most comets approaching the Sun begin to release gas as their ice warms. The surface cracks, jets form, dust clouds spread out into a glowing coma around the nucleus. But 3I, Atlas, looked quiet, too quiet. At first, astronomers assumed the object might simply be small, maybe only a few hundred meters across. But brightness measurements suggested something larger, much larger, something around 1 kilometer wide. A body that size should have produced a far brighter coma. Yet the cloud around it remained thin and faint. That was the first clue, not a shocking one, just a small inconsistency, the kind scientists note quietly and move on. But then the rotation measurements came in. Astronomers track how the brightness of an object changes over time. If it spins, different surfaces reflect sunlight differently. The brightness rises and falls in a pattern. Usually the pattern is smooth, predictable. But the brightness pattern of 3I, Atlas, looked messy, uneven, like the object was tumbling. Not rotating smoothly like a spinning top, but flipping chaotically through space. That kind of motion has a name. Non-principal axis rotation. Imagine throwing a hammer into the air. It does not spin neatly. It flips in unpredictable ways. That is the kind of motion astronomers were seeing. It reminded them immediately of Oumuamua, which had shown the same strange tumbling behaviour. But tumbling alone is not impossible for a comet. Collisions or uneven heating can cause it. So researchers kept collecting more data. And then one of the most powerful instruments ever built turned its attention toward the visitor, the James Webb Space Telescope, floating nearly 1.5 million kilometers away from Earth. Parked at a gravitational balance point called L2, there, far from our planet's heat and light, Webb can observe the faint infrared glow of objects across the universe. Infrared light reveals temperature, structure, composition, things invisible to ordinary telescopes. When Webb locked onto 3I, Atlas, astronomers expected to see a cold lump of ice slowly warming as it approached the sundae. But the thermal data that came back looked strange. The heat distribution across the object was uneven, not just across the surface, but deeper, inside the nucleus itself. This was surprising. Comets are usually loose piles of ice and rock. Think of them like frozen gravel held together weakly by gravity. They are porous, fragile, full of empty spaces. Heat moves through them slowly, but the thermal map from Webb hinted at something different. Something denser, something more compact, almost like the core of the object was a solid body instead of a loose cluster of material. Astronomers ran the models again, then again. Each time, the results suggested the same thing. The nucleus of 3I, Atlas, might not be structured like a typical comet at all. That alone would make it unusual. But the next anomaly raised even more questions, because the object's path began to shift slightly, not dramatically, just enough for researchers to notice. Comets sometimes drift off their predicted paths because gas escaping from their surface acts like tiny rocket thrusters. The effect is called non-gravitational acceleration. It is common, but in this case, something did not match. The acceleration appeared too smooth, too steady. Normally, gas jets are chaotic. They flare, they weaken, they change direction as the comet rotates. But the motion of 3I, Atlas, looked almost consistent, like a gentle push applied over time. Yet telescopes could not see the gas responsible for that push. No massive jets, no bright plumes, just a faint haze. Astronomers at the Harvard-Smithsonian Center for Astrophysics began comparing the data with earlier interstellar observations. They revisited the debate surrounding Oumuamua. One theory suggested hydrogen ice could cause acceleration without producing visible gas clouds. Hydrogen is extremely light and hard to detect, but hydrogen ice has a problem. It evaporates extremely quickly when exposed to sunlight. A body, made mostly of hydrogen ice, should have disappeared long before reaching the inner solar system. Another proposal suggested nitrogen ice. Similar to the frozen surface of Pluto, nitrogen can produce thrust with very little dust, but the spectroscopic readings from Webb did not show the expected nitrogen signature. Each explanation solved one piece of the puzzle, but broke another. And while these debates were happening, researchers began examining another source of information. Voyager 1. The spacecraft launched in 1977 that has now travelled beyond the outer boundary of the Sun's influence, more than 24 billion kilometres away. Voyager's instruments measure the density of dust and particles in interstellar space. That data tells us something important. The space between stars is not completely empty. Tiny grains of dust move through it at enormous speeds. Over millions of years, those particles should erode fragile objects, shatter them, break them apart. Yet 3I, Atlas, appeared remarkably intact, which raised a quiet question among researchers. If this object had travelled through interstellar space for millions of years, how had it survived without being destroyed? The models suggested something unsettling. Perhaps the object was stronger than normal comet material, much stronger. Meanwhile, Webb kept collecting infrared data. And hidden deep in that data, scientists noticed a faint signature, a narrow thermal emission line, very precise, coming from somewhere inside the nucleus. At first, they assumed the signal was noise. Telescopes that's sensitive can produce artifacts, so the engineers recalibrated the instruments. They checked the sensors. They repeated the observation. The signal appeared again. Same wavelength, same position, deep within the core of the object. And that was when the real mystery began. because no known comet material should produce that kind of emission signature. Ice does not behave that way. Dust does not behave that way. Even metallic minerals normally found in asteroids did not match the signal. Something inside the nucleus was producing heat in a very specific way. Not much heat, just enough for Webb to detect, but enough to force scientists to ask a difficult question. What exactly was hidden inside the nucleus of 3I Atlas? And that is where the story starts becoming even stranger. Because when astronomers tracked the object's rotation over the following weeks, the speed of that rotation began to change. Very slowly, but measurably, and the change required energy. Energy that should have come from gas jets. Yet the jets were not there, which meant either the jets were invisible to our instruments, or something else was affecting the object's motion. Something inside it. Something deep within the nucleus that telescopes could not directly see. And as the object continued drifting closer toward the sun, scientists around the world prepared for one thing: more data, more observations, more clues. Because every hour 3I Atlas spent inside our solar system was another chance to understand what it really was, and what they would discover next would raise an even bigger question, not about the object itself, but about how long it had been traveling through the galaxy before we ever noticed it. Time is a strange thing in space. On Earth, we measure it in seconds, hours, and years. We count birthdays, watch seasons change, and feel the slow passing of decades. But objects drifting between stars experience time very differently. A rock ejected from another solar system might wander through the galaxy for 10 million years before passing near another star. 10 million years moving silently through darkness so cold that atoms barely vibrate. During that journey, nothing guides it. No engines, no navigation, just gravity and momentum. So when scientists study an interstellar object like 3I, Atlas, one of the first questions they ask is very simple. Where did it come from? That question sounds straightforward, but the answer is incredibly difficult to calculate. To trace the path of an interstellar visitor, astronomers must reverse its orbit through the galaxy. They must consider the gravitational pull of stars, the slow movement of our Milky Way, and the chaotic motion of objects that have been drifting for millions of years. It is like trying to track a grain of sand blown across an entire continent. But modern computers can simulate these paths with surprising accuracy. Researchers began running orbital models using databases maintained by the European Space Agency and the Harvard-Smithsonian Center for Astrophysics. They compared the incoming velocity of 3I Atlas with known stellar motion recorded by the Gaia spacecraft. Gaia has been mapping the positions and movements of more than 1 billion stars in our galaxy with extraordinary precision. With that data, astronomers can sometimes identify the region of space an interstellar object might have originated from. But when the first simulations finished running, the results were frustrating. There was no obvious source, no nearby star system that matched the object's velocity and direction. Instead, the models suggested something else. 3I. Atlas had likely been wandering through interstellar space for an extremely long time, possibly tens of millions of years, maybe even longer, and that meant something important. If the object had survived that journey intact, it must be far more durable than most comet material. Because interstellar space, despite its emptiness, is not gentle. Tiny particles travel through it at incredible speeds. Even microscopic dust grains can act like bullets when two objects collide at tens of kilometers per second. Over millions of years, those impacts should gradually erode fragile bodies, break them apart, turn them into clouds of debris. Yet here was an object nearly a kilometer wide, still holding together, still spinning, still drifting, as if the journey had barely affected it. Astronomers studying the thermal data from the James Webb Space Telescope began looking deeper into the object's internal structure. Infrared wavelengths can reveal subtle differences in heat capacity and density. Different materials warm and cool at different rates, and those differences can hint at what lies beneath the surface. The maps produced by Webb showed something unusual. The outer layers of the object behaved like typical comet material, cold, dusty, low density, but deeper down, the heat patterns suggested a much more solid structure, something compact, something that conducted heat more efficiently than loose ice and dust should. One possible explanation was that the comet had a rocky core surrounded by icy layers. That idea was not impossible. Some comets may form that way, but the density estimates suggested something even more solid than ordinary rock, almost metallic in behavior. Still, scientists remained cautious. Infrared data can be tricky to interpret. Temperature gradients, surface texture, and rotation all affect the readings, so the Webb team coordinated with other observatories. The Hubble Space Telescope joined the effort, focusing its spectrograph on the faint coma surrounding the object. Hubble has decades of experience analyzing comet chemistry. Its instruments can detect even trace amounts of certain molecules. But again, the results were strange. Water vapor was present, but weak. Carbon monoxide levels were lower than expected, and carbon dioxide, which usually dominates comet emissions near the Sun, appeared unusually scarce. The chemical fingerprint of 3I, Atlas, did not match typical comets from our own solar system. That alone was not shocking. After all, this object formed around another star. Its chemistry could easily be different, but the absence of expected gases made it harder to explain the object's steady acceleration. Without large gas jets pushing against it, what was altering its motion? The question became more urgent as astronomers tracked its rotation more closely. The tumbling motion seen earlier had not stopped, but something else was happening now. The spin rate was slowly increasing, very slightly, but consistently. To visualize what that means, imagine holding a basketball in space and giving it a gentle spin. With no friction, it would keep rotating forever at the same speed. The only way for that speed to change is if some force pushes on it. In comets, that force usually comes from gas jets erupting from the surface. But again, telescopes were not seeing strong jets, only a thin haze of dust. Researchers at the Jet Propulsion Laboratory in California began modeling possible internal processes that could cause such a change. One theory suggested that uneven heating from sunlight might be triggering internal gas pockets beneath the surface. These pockets could vent through tiny cracks too small to produce visible plumes. But the energy required for the observed spin change was still larger than the models predicted. which meant the object was either releasing more gas than we could detect or something else was happening inside. And that possibility led scientists back to the unusual thermal signal Webb had detected earlier. The narrow infrared emission line, still faint, still unexplained, but persistent. Astronomers began examining whether certain metallic minerals might produce that signal when heated. Nickel, iron, magnesium-rich compounds. These elements exist in asteroids, but finding them concentrated inside an interstellar comet would be unusual, not impossible, just rare. Meanwhile, another piece of the puzzle began to emerge from radio observations. Large radio telescopes around the world attempted to detect any signals reflecting from the object. While the famous Arecibo Observatory had collapsed years earlier, other facilities continued the search. The Green Bank Telescope in West Virginia and the Deep Space Network antennas used for spacecraft communication both attempted radar measurements. Radar observations can reveal surface roughness and density. But 3I, Atlas, was extremely far away, making the signals weak. Still, the reflections suggested a surface that was not as porous as typical comet material. The radar brightness hinted at something harder, more reflective, almost like stone rather than snow. None of these clues alone were enough to draw dramatic conclusions, but together they painted a picture that was increasingly difficult to ignore. This interstellar visitor did not behave like the comets astronomers were used to studying. Its chemistry was unusual. Its rotation was changing in unexpected ways. Its internal structure appeared more compact than predicted. And deep inside the nucleus, something was producing a thermal signal that scientists still could not identify. By this point, the scientific community had begun paying close attention. Papers started appearing on preprint servers. Researchers debated possible explanations during late-night conference calls. Most discussions stayed grounded in known physics. That is how science works. Extraordinary claims require extraordinary evidence. But even the most cautious scientists admitted something quietly. 3I, Atlas, was weird, and the closer it came to the Sun, the more data telescopes would gather, which meant the mystery was far from over. Because in the coming weeks, as the object continued its journey through the inner solar system, something else would change. Something subtle at first, then unmistakable. The brightness of the object began to fluctuate in a new pattern, not just because of rotation, but because something on the surface was slowly waking up, something that had remained dormant for millions of years. And when that process finally became visible to our telescopes, the data it produced would open an entirely new chapter in the investigation of 3I, Atlas. At first, no one thought much about the brightness changes. Comets often behave unpredictably when they move closer to the Sunday. Ice warms, cracks form, gas escapes through new vents, and the surface begins to shed dust like a shaken blanket. The process can look chaotic from millions of kilometers away. Brightness rises and falls as different parts of the nucleus face the Sunday. So when astronomers noticed the light curve of 3I, Atlas, becoming slightly more dramatic, the initial reaction was simple. The comet was waking up. That is what normally happens. But as the days passed and more telescopes joined the observation campaign, the pattern in the brightness began to look less random than expected. Usually, when a comet becomes active, Its brightness increases gradually as the sun heats the ice. Jets appear in irregular bursts, sometimes growing stronger when the object rotates and a particular vent faces sunlight. The result is messy, unpredictable flickering. What scientists saw in the case of 3I, Atlas, was different. The fluctuations seemed to follow a repeating cycle. Not perfectly regular, but regular enough that computers could detect the pattern. At first, the cycle looked connected to the object's tumbling rotation. That would make sense. If a bright patch of exposed ice faced the sun every few hours, it would release gas and dust each time it rotated into sunlight. But when astronomers at the Keck Observatory compared the brightness changes with the measured rotation rate, something did not match. The timing was slightly off. The brightness spikes were not lining up with the rotation in the way normal comet jets would. Something else seemed to be controlling the activity. To understand why that bothered scientists, imagine watching a lighthouse from far away. If the lighthouse rotates once every 10 seconds, the light will flash every 10 seconds. The timing is predictable because the motion of the tower controls the light. But what if the flashes happened every 9 seconds instead, or every 11 seconds? Suddenly, the pattern would no longer match the rotation. That is essentially what researchers were seeing. The brightness spikes of 3I, Atlas, were drifting slightly away from the object's spin rhythm, which meant the cause of those flashes might not be tied to the surface facing the sunday. Instead, the activity could be linked to something happening beneath the surface, something internal. This idea made scientists revisit the thermal maps produced by the James Webb Space Telescope. Those maps had already hinted at unusual heat distribution inside the nucleus. Now researchers began analysing them with fresh attention. The deeper they looked, the more interesting the results became. Normally, the inside of a comet warms slowly. Heat from sunlight penetrates only a few meters into the surface before fading away. The interior remains extremely cold, sometimes colder than -200 degrees Celsius. But Webb's infrared data suggested that some parts of the interior of 3I, Atlas, were warming faster than expected. That meant heat was traveling inward more efficiently than it should. Loose ice and dust do not conduct heat very well. Solid materials do, which again pointed toward a dense structure inside the nucleus, a structure capable of spreading thermal energy more effectively than a typical comet. Researchers began modelling what that interior might look like. One possibility was that the object had formed inside a protoplanetary disk rich in heavy elements. Perhaps it started as a rocky body that later accumulated icy layers around it. That would produce a solid interior surrounded by frozen material. But even that explanation struggled to match the observed density estimates. The numbers kept suggesting something stronger than ordinary rock. At the same time, the object's steady, non-gravitational acceleration continued, small but persistent. By this point, astronomers at the Jet Propulsion Laboratory had run dozens of simulations trying to explain the motion. Some models involved hidden gas jets emerging from cracks too small for telescopes to see. Others considered exotic types of ice rarely found in our solar system. Each theory solved part of the puzzle, but left other pieces unexplained. And then something new appeared in the data. A tiny plume, not a large comet tail. Just a narrow stream of material briefly visible in high-resolution images taken by the European Southern Observatory's Very Large Telescope in Chile. The plume lasted only a few hours before fading. But during that time it revealed something important. The material coming off the surface did not spread outward like ordinary comet dust. Instead, it appeared unusually focused, like a narrow jet. That observation triggered immediate excitement among astronomers. Jets are common on comets, but their shape and direction can reveal a lot about what lies beneath the surface. When scientists traced the direction of the plume backward to its origin point on the nucleus, they found something unexpected. The jet did not seem to come from a large exposed ice patch. Instead, it appeared to originate from a small, sharply defined area, almost like a vent. Images from Hubble showed the same location brightening slightly as the comet rotated. This suggested the presence of a localized active region. But the location of that region raised a new question, because it appeared to sit almost exactly above the strange thermal emission Webb had detected earlier. The mysterious signal from deep within the nucleus. For the first time, two different clues were pointing to the same spot. Something beneath that region of the surface might be driving the activity. And if that was true, the internal structure of 3I Atlas might be far more complex than anyone initially believed. Meanwhile, astronomers studying the object's motion through space began comparing its path with archived data from older surveys. The idea was simple. Maybe 3I. Atlas had been seen before without anyone realizing what it was. Older sky images often contain faint objects that were ignored at the time. If the object had been visible earlier in its journey, it might provide a longer record of its behavior. Researchers began digging through old observations from the Sloan Digital Sky Survey and other sky mapping projects. Weeks passed as software scanned enormous databases containing millions of images. Eventually, a possible match appeared. A faint moving object captured in a survey image years earlier. The position was uncertain, but the trajectory matched closely with the projected path of 3I Atlas. If the identification was correct, it meant astronomers now had a much longer timeline of the object's movement. And that timeline revealed something remarkable. The object had been accelerating slightly even before it entered the inner solar system. That detail was subtle but important. Solar heating could not explain acceleration occurring far from the sunday, which meant the force acting on the object might not be purely related to sunlight. Scientists approached this result cautiously. Data from older images can be noisy, but the possibility raised a deeply interesting question. Could something inside the nucleus be generating energy on its own? At this stage, most researchers still favored natural explanations. Radioactive elements embedded within the object could produce small amounts of heat over long periods of time. Internal stresses might also release energy as the comet's structure slowly shifted, but those ideas were still being tested. And while the debate continued, the comet itself kept moving closer to the sunday. With each passing day, the sunlight striking its surface became stronger. The thin haze surrounding it grew slightly brighter, and the narrow vent seen earlier began releasing material more frequently. Each time it did, the brightness spike appeared again in the light curve. That repeating cycle astronomers had noticed earlier. It was becoming clearer now. Something inside the nucleus was heating up. Something buried deep beneath the frozen crust that had likely remained unchanged for millions of years. And as that internal region warmed, pressure was building. Gas trapped beneath the surface was finding pathways to escape. The more scientists watched the object, the more it seemed as if 3I Atlas was slowly waking from a very long sleep. But the most surprising discovery had not happened yet, because during one of Webb's longest observation runs, when the telescope stared at the object for nearly 10 continuous hours, the infrared instruments detected a second emission line, fainter than the first, but unmistakable. And when researchers compared the wavelength of that signal with known chemical signatures, they found something that made several of them pause, not because it proved anything extraordinary, but because it pointed toward a material rarely seen in comet nuclei, a material that behaves more like metal than ice. And if the interpretation was correct, it suggested that somewhere inside the nucleus of 3I, Atlas, there might be a structure far denser than anyone originally imagined. The second emission line forced astronomers to slow down. When scientists see something strange in data, the first instinct is never excitement. The first instinct is doubt. Instruments fail. Sensors drift. Cosmic radiation sometimes hits detectors and creates signals that are not real. So before anyone even discussed what the signal might mean, engineers working with the James Webb Space Telescope did something routine but critical. They checked everything, every calibration file, every sensor temperature reading, every background noise filter. The observation was repeated. Different exposure settings, different observation angles, different time windows. And every time Webb looked again, the faint infrared signature returned. Same wavelength, same region inside the nucleus. At that point, the signal could no longer be dismissed as noise. Something inside the object was producing it. The next step was comparison. Astronomers maintain massive libraries of spectral fingerprints. Every known chemical element and compound leaves a unique pattern in light. When heated, atoms emit specific wavelengths, like fingerprints glowing in the dark. Scientists began matching the mysterious signal against thousands of known materials. Most results came back empty. Ice compounds did not match. Silicate rock did not match. Organic molecules common in comets did not match. Then, one of the researchers ran the signal through a database normally used for asteroid mineral studies. That is when a possible match appeared. Not a perfect match, but close. Certain alloys containing nickel and iron can produce emission patterns in the same range when heated to specific temperatures. Now, this did not mean the object contained metal structures. Nickel and iron exist naturally in space. Meteorites on Earth are often rich in these elements. Some asteroids are even composed almost entirely of metal. But finding such material buried inside an interstellar comet would still be unusual. Most comets form far from their stars in cold regions where ice dominates. Metal-rich bodies usually form closer to stars where temperatures are high enough for heavy elements to condense. So how would a metal-rich structure end up wrapped in layers of ice? One possibility was collision. Long ago, in another star system, a rocky or metallic body might have collided with a comet-like object. The impact could have embedded dense fragments inside the icy mass. Over time, additional ice could have frozen around the debris, forming the object now drifting through space. That explanation seemed reasonable, but it raised another question. If the object contained metal fragments, why was the thermal signal so focused? Why did the emission appear to originate from a narrow region rather than spreading across the entire nucleus? The heat pattern suggested a localized source, almost like a concentrated pocket of material rather than scattered fragments. And that pocket appeared to sit directly beneath the surface vent that had been releasing gas earlier. The two anomalies were clearly connected. Meanwhile, as the object approached closer to the Sun, its faint coma began growing slightly brighter. This was expected. Sunlight warms the surface, causing buried ice to sublimate into gas. Dust trapped in that gas escapes into space, forming the glowing halo around the comet. But again, the behavior of 3I, Atlas, did not fully match typical comet activity. Instead of multiple jets appearing randomly across the surface, most of the visible activity seemed to come from only a few locations. 3 small active regions had now been identified, and one of them was significantly stronger than the others. That was the same region associated with the infrared anomaly. Astronomers began calling it the primary vent. High-resolution images taken by the Very Large Telescope in Chile showed a thin stream of dust emerging from that spot every few hours. Each time it happened, the brightness spike appeared again in the light curve. The pattern was now clear. The activity was periodic. Something beneath the surface was heating up, releasing gas through that vent, then cooling again before the cycle repeated. The timing of the cycle was about 9 hours, but the object's rotation period was closer to 8 hours. That difference remained puzzling, because if sunlight were responsible for the heating, the vent should activate once every rotation when the surface faced the Sunday. Instead, the timing drifted slightly, almost like the internal heating source had its own rhythm. That observation triggered new modeling efforts at the Jet Propulsion Laboratory. Engineers began simulating different internal structures that could produce such behavior. One idea involved trapped volatile gases. If a pocket of gas deep inside the comet was slowly warming, pressure could build until it forced gas through the vent. After the release, the pocket would cool slightly before the cycle began again. This mechanism could explain the periodic activity, but it still did not explain the metallic emission signature detected by Webb. Unless that metallic material was somehow acting like a heat conductor, channeling warmth from deeper layers toward the vent. And that possibility introduced an interesting thought. What if the core of 3I, Atlas, was not made entirely of ice? What if it had a rocky or metallic center surrounded by frozen material? In that case, the metallic interior could absorb sunlight more efficiently and distribute heat inward. The internal gas pocket theory would become far more plausible. For a while, this explanation seemed promising. But then a different piece of data complicated things again. Astronomers working with the Green Bank telescope attempted another radar observation. Radar is extremely useful for studying asteroids near Earth, but interstellar objects are much farther away, making radar reflections weak. Still, by combining multiple signals, researchers managed to obtain a rough estimate of the object's surface reflectivity. The results were surprising. the radar reflection was stronger than expected for a dusty comet surface. It suggested a harder outer layer, possibly crusted ice mixed with rock, or something even denser. Again, this was not impossible. Comets sometimes develop crusts after repeated heating cycles. But 3I, Atlas, had never visited our solar system before. Its surface should have remained relatively untouched by strong sunlight, unless it had already passed close to another star long before arriving here. And that thought returned scientists to the question of its origin. Where had this object actually come from? New orbital simulations began running on powerful supercomputers. Using star movement data from the Gaia mission, researchers traced the object's incoming trajectory backward through time. They tested thousands of possible paths across the Milky Way. Some simulations suggested the object may have passed near a dense region of stars millions of years ago, possibly within a young stellar cluster. Clusters are chaotic places. Stars form close together, gravitational forces pulling objects in every direction. Planets and comets can be ejected into interstellar space by close encounters. If 3I, Atlas, originated from such an environment, its unusual composition might make sense. Perhaps it formed near a metal-rich asteroid belt before being thrown outward into colder regions where ice accumulated around it. Over time, the object could have grown into a strange hybrid body. Part comet, part asteroid. That explanation was now gaining support among many astronomers. It accounted for the metallic spectral signature. It explained the dense interior suggested by Webb's thermal data, and it provided a plausible formation scenario. But even with that model, one mystery remained unsolved: the internal heating cycle, the 9-hour rhythm driving the vent activity. Solar heating alone could not produce that timing difference. So researchers turned their attention to another possibility: rotation combined with internal heat conduction. If the interior contained metal-rich material, heat might travel through it in ways different from normal comet ice. Instead of warming only the sunlit surface, heat could slowly spread deeper inside before reaching the vent region. This delayed conduction could produce a repeating cycle slightly offset from the object's rotation. In other words, the vent might activate not when sunlight hit it directly, but hours later when heat finally reached the buried gas pocket. Computer models began testing this idea. Early results looked promising. The 9-hour cycle could indeed be reproduced if a dense core conducted heat slowly outward through surrounding ice. The theory was still preliminary, but it was the first explanation that connected all the major clues. The metallic emission signature, the dense interior, the delayed vent activity. For now, it seemed the mystery might finally have a natural solution. But the story was not finished yet, because while scientists were busy studying the object's internal structure, something else was quietly happening far above the surface. The comet's faint tail, barely visible before, had begun stretching farther into space. And within that thin stream of dust and gas, spectrographs soon detected something that had not appeared in earlier observations. A molecule rarely seen in comets, a molecule that forms only under extremely specific conditions. When the first analysis confirmed its presence, several researchers realized that the history of 3I Atlas might be far stranger than anyone had imagined. At first, the signal appeared so faint that most astronomers ignored it. Spectrographs are incredibly sensitive instruments. They split incoming light into thousands of tiny wavelength bands, and within those bands, scientists search for patterns that reveal the presence of molecules. But faint lines can appear for many reasons. Dust particles can scatter light, cosmic radiation can strike detectors, even Earth's atmosphere can introduce contamination when ground telescopes observe distant objects. So when the unusual molecular line first appeared in the data coming from the Very Large Telescope in Chile, researchers treated it cautiously. They marked it, saved it, and moved on. But over the next several nights, the same signal appeared again. Then again, each time the comet rotated and the narrow vent released its small plume, the spectral line brightened briefly before fading. That pattern caught the attention of a small group of scientists studying volatile compounds in comet tails. Because the molecule that seemed to match the signal was not one normally found in comets, most comets contain simple molecules. Water vapor dominates. Carbon monoxide and carbon dioxide are common. Small organic molecules sometimes appear as well, remnants from the early days of planetary formation. But the new signal suggested something slightly more complex: phosphorus-bearing compounds. Phosphorus is not rare in the universe, but it does not usually appear in large amounts in comet gas. When it does show up, it is often locked inside minerals rather than floating freely in vapor form. Yet here, in the thin stream escaping from the vent of 3I Atlas, the spectrograph readings hinted at a gaseous phosphorus compound briefly escaping into space before freezing again in the cold vacuum. Scientists wanted confirmation, so they asked the Atacama Large Millimeter Array, known as ALMA, to join the observation campaign. ALMA sits high in the Chilean desert, made up of dozens of radio antennas working together as a single giant telescope. It specializes in detecting faint molecular emissions across the cosmos. When ALMA targeted 3I, Atlas, during one of the vent cycles, the array detected the same spectral signature, weak but unmistakable. Phosphorus compounds were indeed present in the plume. This discovery added another layer to the mystery. Phosphorus is an important element in chemistry, especially in biological molecules on Earth. It forms part of DNA and many cellular structures. But its presence alone does not imply anything extraordinary. In space, phosphorus can form naturally inside certain minerals or appear in molecular clouds where new stars are born. The interesting part was not the element itself, it was where it was appearing. The vent releasing gas from 3I Atlas seemed to be tapping into a reservoir deep inside the nucleus where unusual materials had accumulated. And that raised a question about the object's formation. If the interior contained both metallic compounds and phosphorus-rich material, perhaps it formed in an environment very different from the distant icy regions where comets typically originate. Astronomers began revisiting the orbital simulations again. Using improved trajectory calculations, they traced the object's path backward through the Milky Way over tens of millions of years. The further back the models went, the more uncertain the results became. Tiny errors in velocity multiply over time, making long-term paths difficult to reconstruct. But several simulations kept pointing toward the same region of space, a dense stellar environment located thousands of light years away, a region known for forming massive stars. Massive stars burn brightly and live short lives. When they die, they explode as supernovae, scattering heavy elements across surrounding space. That process enriches nearby planetary systems with metals and complex compounds. If 3I, Atlas, formed in such an environment, it might explain its unusual composition. Metal-rich debris from earlier generations of stars could have mixed with icy material forming far from the heat of a young sun. Over time, collisions might have embedded dense fragments within the growing comet. Eventually, a gravitational disturbance, perhaps a passing star, could have ejected the object into interstellar space. Once free, it would wander through the galaxy for millions of years until gravity from our Sun captured its path temporarily. This explanation satisfied many scientists. It accounted for the metallic signature detected by Webb. It explained the presence of unusual molecules in the vent plume, and it fit with what astronomers know about chaotic environments around young stars. Still, some questions remained. One of them involved the timing of the vent cycles. The 9-hour rhythm continued. Every 9 hours, the plume appeared again. Every 9 hours, the brightness spike returned. And each time, the phosphorus signature briefly strengthened before fading into the background. If the heating came from sunlight conducted through the interior, the timing should slowly shift as the comet moved closer to the Sun and temperatures changed. But the cycle remained almost perfectly stable. 9 hours. Again and again. Researchers at the Jet Propulsion Laboratory noticed this stability while comparing observation logs. One of them ran a quick analysis of the plume timing over several weeks. The pattern held steady, which meant whatever process was driving the vent activity was remarkably consistent. Natural systems can sometimes produce such regularity, but in comets it is rare. Most comet jets fluctuate wildly. Surface cracks, expand, dust clogs vents. New fractures appear without warning, yet the primary vent on 3I Atlas behaved almost like a heartbeat, slow, steady, predictable. This observation sparked quiet discussion among scientists studying comet physics. Some suggested that the vent might connect to a deep chamber containing volatile gas trapped beneath a strong crust. If that chamber filled and emptied in a stable cycle, the timing might remain consistent. Others proposed that thermal waves travelling through the dense interior might reach the vent region at regular intervals. Both explanations were possible, but neither had been observed clearly before in an interstellar comet. Meanwhile, the object continued its journey inward. The sun's light grew stronger. The faint tail stretched farther behind it, forming a delicate stream of dust drifting across millions of kilometers of space. Through powerful telescopes, the tail appeared almost ghost-like, a thin ribbon glowing softly against the blackness. And within that ribbon, scientists began spotting something else. Tiny fragments, small particles breaking away from the nucleus and drifting into the tail. Fragmentation is common for comets nearing the sunday. Heat stresses the surface, causing pieces to break off. But the pattern of fragments in 3I Atlas looked unusual. Instead of random debris scattering in all directions, most fragments seemed to originate near the same active vent. Each time the vent erupted, a small cloud of particles followed, almost like dust being blown from a narrow pipe. The fragments were small, likely no larger than pebbles, but their repeated appearance confirmed something important. The vent was gradually carving a channel through the surface. Each burst of gas carried away more material, slowly widening the opening. As that opening grew larger, telescopes might eventually glimpse deeper into the region where the strange thermal signal originated. And if that happened, the mystery hidden inside the nucleus might finally reveal itself. Astronomers around the world continued watching. The James Webb Space Telescope, the Keck Observatory, the Very Large Telescope, and ALMA all scheduled additional observation windows. Because every hour mattered. 3I. Atlas was moving fast. In a matter of months, it would swing around the sun and begin leaving the solar system again. Once it travelled far enough away, even the most powerful telescopes would lose sight of it, which meant this brief passage was humanity's only chance to study the object up close. And just as the vent opening began widening enough for deeper observation, the Webb telescope prepared for one of its most detailed scans yet. A long infrared observation designed to map the internal heat patterns of the nucleus with higher resolution than before. Scientists hoped the new scan might finally clarify the nature of the dense structure buried inside the comet. But when the data from that observation arrived, the images revealed something no one had expected to see. Something that suggested the interior of 3I, Atlas, might not be as simple as a solid core surrounded by ice. Instead, the heat map hinted at a shape, a structure. Something with boundaries that looked almost geometric. For several minutes after the new infrared maps arrived from the James Webb Space Telescope, the room at the data center stayed quiet. No one rushed to conclusions. No one said anything dramatic. Because in astronomy, the first rule when something looks strange is simple. Assume you are wrong. Webb's detectors are incredibly sensitive. A tiny processing error can produce shapes in the data that are not actually there. Cosmic rays can strike sensors. Background heat from distant stars can bleed into an observation. So the first thing the team did was check the calibration again. Every pixel, every noise filter, every alignment correction. The data pipeline was run from the beginning. Hours passed while computers reprocessed the infrared frames. When the corrected map finally appeared again on the screen, the strange pattern was still there. And now it looked even clearer. Inside the nucleus of 3I, Atlas, beneath layers of cold ice and dust, the heat distribution formed something unusual, not random, not smooth, but shaped. The warm region seemed to trace lines that intersected at angles sharper than natural fractures usually produce. To understand why that was unsettling, imagine taking an X-ray of a rock. Normally, you would expect to see irregular cracks, pockets of air, and messy layers where minerals formed. Nature rarely produces clean geometry on a large scale. But the thermal image of the nucleus showed something different. Several linear boundaries intersecting in a pattern that almost resembled a polygon buried deep inside the object. The lines were faint, visible only because the temperature changed slightly along their edges. But they were there. The first explanation was simple. Fractures. When comets experience temperature changes, internal stresses can crack the ice. Those cracks sometimes spread in networks that resemble geometric shapes. But when scientists compared the angles of the lines, the pattern did not behave like a typical fracture network. Most natural fracture systems form irregular webs. The shapes seen here were more organized, almost symmetrical. Still, no one suggested anything extraordinary. The more likely explanation was that the metallic material detected earlier might have formed solid plates or layers inside the comet. If those layers cooled differently than the surrounding ice, they could create boundaries visible in infrared heat maps. That was the leading theory. And yet, even with that explanation, something about the structure felt unusual. The lines seemed too sharp, too evenly spaced, too coherent for debris trapped randomly inside a comet nucleus. So the team ran another test. They overlaid the thermal map with the rotation model of the object. If the warm structure inside the comet was real, it should move slightly relative to the Sun as the nucleus tumbled through space. The results were fascinating. As the comet rotated, the heat pattern shifted exactly as expected. The structure was real. It was inside the object, not an artifact, not noise. Something buried deep within the nucleus had a shape that was influencing how heat flowed through the comet, and that shape seemed to be connected directly to the vent that had been releasing gas every 9 hours. At this point, the research teams at several institutions began working together. Scientists from the Jet Propulsion Laboratory, the Harvard-Smithsonian Center for Astrophysics, and observatories across Europe started sharing data in real time. Because when different instruments detect clues that point to the same region of an object, it usually means something important is happening there. Webb had detected unusual heat patterns. The Very Large Telescope had identified the vent directly above that region. ALMA had confirmed the presence of phosphorus compounds escaping from that vent. And earlier spectrographic studies had hinted at metallic material buried beneath the surface. All signs pointed toward the same place inside the nucleus, a dense internal structure. But how large was it? To answer that, astronomers tried something creative. Instead of mapping the structure directly, they studied how the comet reacted to sunlight over time. When a body rotates through sunlight, different parts of it heat up and cool down. By carefully measuring those temperature changes, scientists can estimate how quickly heat spreads through the interior. If the inside is loose and porous, heat travels slowly. If it contains dense material, heat spreads faster. Using dozens of infrared measurements collected by Webb, researchers created a thermal model of the entire nucleus. When the model finished running, it produced a surprising estimate. The dense region inside the comet might be hundreds of meters across, possibly nearly half the diameter of the nucleus itself. That was far larger than a small embedded rock. It suggested a massive central structure, almost like a core surrounded by layers of ice, and that raised an intriguing possibility. Perhaps 3I, Atlas, was not originally a comet at all. Perhaps it began as something else. An asteroid-like body formed closer to a star, rich in metal and rock. Later, as it drifted outward into colder regions of its home system, it could have accumulated layers of frozen gas and dust. Over millions of years, the icy shell would grow thicker, eventually turning the object into something that resembled a comet. If such a hybrid body were later ejected into interstellar space, it might look exactly like what astronomers were now observing, a comet-like exterior hiding a dense interior. The theory was gaining traction, but it still did not fully explain the geometric heat pattern seen in the Webb images. Natural asteroid cores rarely produce clean polygon-like boundaries. Still, scientists reminded themselves of something important. Nature can produce strange shapes when materials cool and fracture. Basalt columns on Earth sometimes form hexagonal patterns. Ice crystals can grow into sharp, symmetrical structures. So while the pattern inside 3I, Atlas, looked unusual, it was not impossible, at least not yet. Meanwhile, the comet continued approaching the Sunday. Its tail now stretched across millions of kilometers. From Earth, it appeared only as a faint point of light, barely visible even through large telescopes. But within that tiny dot, enormous processes were unfolding. Each 9-hour cycle, the primary vent erupted again. Each eruption carried more dust and gas into space. And with every burst, the vent opening grew slightly wider. High-resolution images showed the mouth of the vent slowly expanding. The narrow pipe inside the nucleus was eroding. Layer by layer, the frozen crust above the dense structure was being removed. If the process continued long enough, the interior region producing the strange heat pattern might eventually become exposed. Scientists watched closely, because that moment, if it came, could reveal the true nature of whatever lay buried inside the comet. And as the sun's heat continued building, pressure beneath the surface was rising. Gas pockets trapped deep inside the nucleus were expanding. Each vent cycle released some of that pressure, but not all of it, which meant something inevitable was approaching. A larger eruption, one powerful enough to tear away a significant section of the surface. If that happened, telescopes might finally see deeper into the heart of 3I, Atlas. And the next time the vent awakened, the brightness spike would be stronger than anything observed so far. The moment scientists had been quietly anticipating finally arrived on a night when most of the world was asleep. It began with a small change in the brightness data. Astronomers watching the light curve of 3I, Atlas, were used to the steady rhythm by now. Every 9 hours, the object brightened slightly as the vent released gas and dust. The spike would last a short time, then fade as the plume drifted away into space. But during this particular cycle, the spike did not behave the same way. Instead of a quick rise and fall, the brightness climbed higher than usual. Then it kept climbing. At first, the observers assumed it was just a stronger vent cycle. Comets sometimes release bursts of gas when internal pressure builds faster than expected. But within minutes, telescopes around the world began reporting the same thing. The brightness of the comet had doubled, then tripled, a sudden flare. Within the control rooms at several observatories, astronomers quickly realized what was happening. A major outburst. Outbursts occur when gas trapped beneath a comet's surface suddenly breaks through the crust, blasting dust and ice fragments into space. These events can dramatically increase a comet's brightness for a short period of time. But what made this one unusual was where it originated. High-resolution images taken by the Very Large Telescope showed the plume expanding outward from the exact location of the primary vent, the same region that had been slowly widening over the previous weeks. The vent had finally ruptured. What had once been a narrow opening was now tearing into a larger cavity beneath the surface. The plume spreading into space was enormous compared with earlier releases. Dust particles fanned out in a glowing cone, reflecting sunlight and creating the dramatic brightness spike seen from Earth. Astronomers quickly redirected as many instruments as possible toward the comet. The Keck Observatory captured images showing fragments of ice and rock shooting outward at several meters per second. Meanwhile, the James Webb Space Telescope began recording infrared measurements of the expanding plume. What scientists hoped was simple. If the outburst had opened a deeper channel into the nucleus, the escaping gas might reveal more about the hidden structure inside. And almost immediately, Webb sensors detected a surge of thermal energy coming from the exposed region. The heat signature that had previously appeared faint and buried now grew much stronger. The interior cavity was briefly visible in the infrared map, and the shape of that warm structure became clearer. It was not just a rough cluster of dense material. It appeared to form several flat surfaces, meeting at angles, almost like plates arranged around a central point. The geometry still looked natural enough that no one suggested anything extraordinary. But the regularity of the boundaries was difficult to ignore. Nature rarely forms shapes like that inside a comet. Still, the more urgent discovery came from the spectrograph studying the gas cloud. Because the eruption had carried material from deeper inside the nucleus than ever before, and within that material, astronomers detected something entirely new. Complex organic molecules. Not just simple carbon compounds, but chains of atoms more intricate than those usually seen in comet emissions. One group studying the plume with ALMA noticed spectral signatures associated with molecules containing phosphorus, carbon, hydrogen, and oxygen in complex combinations. These compounds are not unique to life, but they are part of the chemical family that can eventually lead to biological molecules. Their presence suggested that the interior of 3I, Atlas, contained materials that had undergone interesting chemical processes long ago, perhaps during the early days of its home star system, perhaps during collisions with other objects rich in organic compounds, or perhaps during long exposure to radiation while drifting through interstellar space. Each possibility pointed to a fascinating story about the object's history, but there was still the question of the dense structure beneath the surface. As the outburst continued, fragments of the crust kept breaking away. The vent opening grew wider. In Webb's infrared images, the exposed region now appeared almost like a shallow pit carved into the comet's surface. Within that pit, the warm structure below became easier to study. Researchers zoomed in on the thermal map, adjusting contrast levels to highlight subtle temperature differences. The polygon-like pattern seen earlier was now unmistakable. 6 boundaries intersected in a shape that almost resembled a distorted hexagon. Inside that shape, the temperature was consistently higher than the surrounding ice, which meant the dense material inside was absorbing and holding heat more effectively than the comet's outer layers. One scientist at the Jet Propulsion Laboratory made a simple observation. If that structure was metallic, it might behave like a thermal battery, absorbing sunlight during one rotation cycle and releasing heat slowly afterward. That could explain the delayed vent timing. The 9-hour rhythm. Sunlight would warm the dense core as the comet rotated. Hours later, the heat would reach the gas pocket beneath the vent. Pressure would build. The vent would erupt. Then the process would repeat. The theory fit the data better than anything else so far. But the question remained, how did such a large metallic structure end up inside a comet? One possibility was that it formed naturally during the early stages of a planetary system. Dust grains containing metal could clump together near a young star, forming asteroid-like bodies. Later, if those bodies migrated outward into colder regions, ice could accumulate around them. Over time, they might become hybrid objects, rock and metal cores wrapped in frozen layers. If gravitational chaos later ejected them into interstellar space, they would wander through the galaxy exactly as 3I, Atlas, had. That explanation satisfied most of the scientific community for now, because although the shape of the internal structure looked unusual, nothing about it proved it was anything other than a natural formation. Nature has produced far stranger things. Still, the more the comet revealed, the more fascinating its story became. The outburst eventually began to weaken. The expanding dust cloud drifted farther away, thinning as it spread across millions of kilometers. The brightness of the comet slowly returned to its previous level. But the vent opening remained larger now, and inside that opening, telescopes could still see the warm glow of the dense structure buried beneath the ice. The internal region that had been hidden for millions of years was now partially exposed to space, which meant future vent cycles would likely become stronger. More material from the interior would escape, and with each eruption, astronomers might learn more about the strange object that had travelled across the galaxy to reach our solar system. But there was one more discovery waiting in the data. A detail so subtle that it took several days before anyone noticed it. While studying the infrared maps frame by frame, one researcher realized that the heat pattern inside the exposed cavity was not completely stable. The structure seemed to be shifting slightly as the comet rotated, not tumbling like the entire nucleus, but adjusting in a slower, almost delayed motion. At first, the change was so small it looked like a processing artifact. But when the frames were aligned and compared carefully, the shift remained. The dense structure inside the nucleus might not be fixed in place. It might be moving very slowly, almost as if the surrounding ice was gradually sliding around it. And if that interpretation was correct, it meant the heart of 3I, Atlas, might not simply be a solid core. It might be something embedded loosely within the comet. Something that had been trapped there for millions of years as the object wandered through interstellar space. Something that was now slowly revealing itself as the comet approached the warmth of our Sunday. By the time the comet reached its closest approach to the Sun, the investigation had turned into something far bigger than anyone expected when that small moving dot first appeared in the Atlas survey data. At first, astronomers believed they were simply watching another interstellar visitor passing through our neighborhood, a rare opportunity to study material from another star system. But the weeks of observation had changed the tone of the entire investigation. Now telescopes across Earth and in orbit were all focused on the same object. Because the deeper scientists looked, the stranger the story became. The widened vent had exposed a portion of the internal structure buried inside the nucleus. Infrared imaging from the James Webb Space Telescope now showed the warm geometric boundaries with far greater clarity than before. The polygon-like pattern stretched across a region nearly half the width of the comet's core. 6 distinct planes, edges intersecting at sharp angles. And along those boundaries, heat flowed differently than anywhere else in the nucleus. It was not the kind of structure normally produced when loose ice and rock simply freeze together. It looked more organized, not perfect, but organized enough that the human brain immediately noticed the pattern. Still, astronomers refuse to jump to wild conclusions. Nature is capable of strange architecture. Crystals form hexagons. Basalt columns on Earth sometimes grow into perfectly aligned pillars. Ice fractures can spread through glaciers in geometric networks. So, the most conservative explanation remained the most likely one. The structure was probably a metallic formation created during the early stages of a distant planetary system, a heavy core wrapped in layers of ice, a cosmic fossil from a place we may never identify. But the final weeks of observation introduced one last piece of evidence that made even cautious researchers pause, because the shifting heat pattern detected earlier did not stop. As the comet rotated through sunlight, again and again, the internal structure continued to move slightly relative to the outer shell, not rotating freely, not tumbling, but sliding, slowly adjusting position inside the icy body. At first, the motion was extremely subtle, just a few centimeters each rotation. But over several days, the shift became measurable. The dense structure inside the comet was not rigidly attached to the surrounding ice. It was embedded, suspended, like a stone frozen inside a block of melting ice. That meant the comet was not a single solid object. It was more like a shell. A frozen container surrounding something heavier trapped within it. When sunlight warmed the outer layers, the ice softened slightly, allowing the interior mass to shift under gravity and rotational forces. And that explained the final mystery, the 9-hour vent cycle, the delayed heating pattern, the strange thermal boundaries. The core inside 3I, Atlas, was acting like a massive heat reservoir, absorbing sunlight when exposed through the thin icy shell, then releasing that heat hours later into the surrounding gas pockets. Each time the pressure built high enough, the vent erupted. A cosmic heartbeat driven by physics rather than sunlight alone. When the final models were completed, most scientists agreed on a scenario that finally tied everything together. Long ago, in a distant star system, a metal-rich asteroid likely formed close to its star. Later, it may have collided with icy bodies drifting farther out. Over time, the fragments froze together, building layers of ice around the dense core. Eventually, a gravitational disturbance, perhaps a passing star or migrating planet, flung the object out of its home system entirely. From that moment on, the hybrid body drifted alone through interstellar space for millions of years. Dust grains struck its surface. Cosmic radiation altered its chemistry. Tiny impacts carved scars into the frozen shell, but the dense metallic heart inside remained intact, silent, cold, carrying with it the chemical memory of a planetary system that may no longer even exist. And then, after wandering across the galaxy for ages beyond human imagination, gravity from our sun pulled it into a temporary visit. A brief encounter with the only civilization capable of noticing it. For a few months, the most powerful telescopes ever built watched this ancient traveler as it woke under the warmth of a new star. They mapped its chemistry, they tracked its motion, they uncovered the hidden core buried inside its frozen body. And now, As it begins its journey back toward the dark between stars, the investigation is almost over. The comet is already moving away from the Sunday. Its activity is slowly fading. The vent cycles are becoming weaker as the internal gas pockets empty. Soon the tail will disappear entirely. In a few years, the object will be too distant for even the James Webb Space Telescope to observe. It will vanish back into the enormous silence of interstellar space. And perhaps millions of years from now, it will pass near another star, another solar system, maybe another planet, with beings capable of looking up and asking the same questions we did. Where did this object come from? What stories are hidden inside its frozen layers? How many other travelers like this are drifting across the galaxy right now, unseen? Because discoveries like 3I, Atlas remind us of something both beautiful and unsettling. Our solar system is not isolated. It is part of a much larger cosmic ocean. Objects drift between stars all the time. Fragments of distant worlds. Pieces of ancient collisions. Messengers carrying chemical clues from places humanity will never reach. And every once in a while, one of those travelers crosses our path just long enough for us to glimpse a tiny part of the story it carries. The universe does not often send visitors, but when it does, they remind us that the night sky is not just full of stars, it is full of journeys. Journeys that began long before humans existed. Journeys that will continue long after we are gone. And somewhere out there, in the cold darkness beyond the reach of our sun, countless other objects like 3I, Atlas, are still moving silently through space, waiting for the day they wander close enough for someone to notice. If you want to keep exploring the strange things entering our solar system and the secrets hidden in deep space, subscribe and continue with the next investigation.